sklearn, linear model, SGD classifier. Description. The SGD classifier in scikit-learn is a linear model that implements stochastic gradient descent (SGD). For classification, it is a versatile and efficient algorithm well suited for large datasets with high dimensionality. Inputs. X. This is the input feature matrix, where each row represents a sample and each column represents a feature. It should be a 2D array or a sparse matrix. Y. This is the target vector, representing the class labels for each sample in X. It should be a 1D array. Outputs. Model. This is the trained SGD classifier model. You can use this model to make predictions on new data points. Predicted labels. This is the output of the predict method, which provides the class labels predicted by the trained model on new data. Steps. Initialization. The algorithm starts by initializing the model's parameters, weights and biases randomly. Iteration. The algorithm iterates through the training data, taking one sample or a small batch of samples at a time. Gradient calculation. For each sample, the algorithm calculates the gradient of the loss function with respect to the model's parameters. Parameter update. The parameters are updated by taking a step in the direction of the negative gradient. The step size is controlled by the learning rate. Repeat steps 2 to 4 are repeated for a specified number of epochs passes through the training data. Metrics. Accuracy. The proportion of correctly classified samples in the test set. Precision. The proportion of correctly classified positive samples among all samples predicted as positive. Recall. The proportion of correctly classified positive samples among all actual positive samples. F1 score. The harmonic mean of precision and recall. Visualization plots. Decision boundary. This plot visualizes the decision boundary learned by the model. It is particularly useful for binary classification problems where the data can be visualized in 2D. Feature importance. This plot shows the importance of each feature in the classification decision, measured by the absolute value of the corresponding weight in the model. Fine-tune parameters. Loss. The loss function used to optimize the model. Common options include hinge for linear SVM, log for logistic regression, and modified Huber for robust regression. Penalty. The regularization term added to the loss function to prevent overfitting. Options include L2 for L2 regularization ridge regression and L1 for L1 regularization lasso regression. Alpha. The strength of the regularization term. Higher values correspond to stronger regularization. Learning rate. The step size taken during parameter updates. Options include constant, optimal, InvScaling, and adaptive. Eta 0. The initial learning rate used when learning rate is set to constant. Uncertainty methods. Confidence scores for probabilistic classifiers such as those with log loss. The model can output confidence scores representing the probability of each sample belonging to each class. These scores can be used to assess uncertainty. Challenges and fixes. Challenge 1. Overfitting. This occurs when the model learns the training data too well, resulting in poor performance on unseen data. Sample use case. A model trained on a small dataset might overfit and struggle to generalize to new samples. Fixes to challenge 1. Increase the size of the training dataset. Add regularization L1 or L2 to the model. Adjust the hyperparameters, such as alpha, learning rate, and eta 0, to find a balance between bias and variance. Challenge 2. Data scaling. The performance of SGD can be sensitive to the scale of features. Features with larger magnitudes can dominate the optimization process, leading to biased gradients and slow convergence. Sample use case: a dataset with features having widely different scales might lead to slow convergence and poor performance. Fixes to challenge 2. Use feature scaling techniques, such as standardization or normalization, to ensure all features have similar scales. Challenge 3. Choice of loss function. The choice of loss function can significantly impact model performance. For example, using a hinge loss for a dataset with outliers might lead to poor performance. Sample use case: training a model with hinge loss on a dataset with outliers might result in a model that is highly sensitive to those outliers. Fixes to challenge 3. Use more robust loss functions, such as modified Huber, if the dataset contains outliers.